Hi friends, welcome to my channel Interesting Engineering. Today in our video we are going to discuss about electrodynamometer type instruments. So in our previous video we have already discussed about PMMC and MI instruments. PMMC instruments are meant for measuring DC values of currents and voltages, whereas MI instruments can measure both AC as well as DC values of currents and voltages. So this instrument, the electrodynamometer type instruments, can also measure AC as well as DC values of currents and voltages. Then what will be the difference between a MI and this electrodynamometer type instrument? This instrument is also called the transfer type instruments. This is because in the case of MI instrument, we need to calibrate it separately for DC measurement and AC measurement. Whereas in this case, once it is calibrated for measuring the DC values, with the same calibration we can able to measure the AC values of currents and voltages also. That's why this instrument is called a transfer type instrument, and this is the major advantage of using this instrument. Now we shall see about the principle of operation of this instrument. Similar to all other types of instruments, these instruments also work on the principle of Faraday's laws of electromagnetic induction. What do you mean by Faraday's law? So when we place a current carrying conductor in a magnetic field, there develops a force which makes the current carrying conductor to move from its initial position. So this is the basic law involved in almost any type of instruments, and here the direction of movement of the conductor can be measured using the Fleming's left hand rule. So any instrument, PMMC, MI or electrodynamometer type instruments, operates on the principle of Faraday's laws of electromagnetic induction. So this is the diagram of this instrument, electrodynamometer type instrument. We shall see about its construction first. So the parts involved in an electrodynamometer type instrument are classified under 6 different categories: fixed coil arrangement, moving coil arrangement, moving system, controlling system, damping system, and the indicating system. So when we look at our diagram, here we have fixed coil arrangements. These are all the fixed coil arrangement, and this is divided into two equal halves. It is divided for the purpose of providing uniform magnetic field, as well as it provides a path for movement of this moving coil. That's why it's divided into two equal halves. Then the moving coil is nothing but the copper coil. We have number of turns of copper coil wound on a non-metallic former, mainly aluminium former. So this is the moving coil used here, and this moving coil is pivoted on a aluminium spindle, which is nothing but the moving system in this instrument. And to the bottom of this moving coil we have a spring arrangement. So in these instruments there develops 3 important torques for its operation. One is the deflecting torque, controlling torque, and the damping torque. So in these instruments, for its movement, for the movement of pointer and scale arrangement, there needs a force. That force is nothing but the deflecting torque, and to oppose that force, to bring back the pointer to a steady position, we make use of a controlling torque, and the pointer's oscillation is reduced to 0 by means of a damping arrangement. So to provide a controlling force, we make use of a spring arrangement. A spring is directly connected at the bottom of this moving coil, which produces a force in the opposite direction of the force developed to deflect this moving coil. So that spring arrangement provides the controlling force here, and for the purpose of damping we make use of air friction damping in this instrument. So air friction damping is developed by means of moving a piston inside a aluminium cylinder. So that provides a damping force for the movement of this pointer. And the last system is the indicating system. So here in this instrument we make use of a pointer and scale arrangement. So this acts as the indicating system, and this pointer and scale arrangement, the scale is a non-uniform scale arrangement is made use of in this electrodynamometer type instruments. So now we shall see about its operation. Similar to MI instruments, here we make use of a electromagnet. So the electromagnet is developed by means of passing current through these fixed coils. So when we pass current through these fixed coil arrangement, there develops magnetic field. So in this magnetic field, here this is a uniform radial magnetic field. So in this magnetic field, when we place a moving coil here, this moving coil will be having this moving coil is also connected in series with this fixed coil arrangement. So when we pass current through this fixed coil, it enters into this moving coil also. So this is a current carrying conductor, and this fixed coil develops an electromagnetic field. So when this current carrying conductor is placed in a magnetic field, there develops a force. So that force makes the moving coil to deflect from its initial position. So it deflects at an angle theta. So that deflection will have to be controlled by means of spring arrangement provided at the bottom of this moving coil. So this spring will be changing its position, will be relaxing, so that it will develop a opposing force on this moving coil, so that the movement of this coil will be controlled by means of the spring arrangement provided here. So when these two forces, that is the deflecting force, is balanced by the controlling force, the pointer will be at a steady position, that is it remains at a single particular position on the scale arrangement, which is a measure of amount of current entering into this fixed coil. So by means of which we can able to measure the current entering over here. So this is the working of this instrument, and these instruments we can make use of for measuring currents, voltages, power factor. With making some little bit modification in this circuit, we can able to measure even power factor also. So this is about the working of this instrument. Now we shall see the torque equation of this instrument. So now we shall derive at the electrodynamometer type instruments torque equation. So this diagram is a representation of electrodynamometer type instrument. Since we have two coil arrangement in these instruments, it is represented in this manner. So this represents the fixed coil, and this represents the moving coil. The inductance, self-inductance of fixed coil is denoted by L1, and the self-inductance of moving coil is denoted by L2. The current entering at the fixed coil is represented by means of I1, and the current developed in the coil 2 is denoted by means of I2. So V1 is the voltage across the fixed coil, and V2 is the EMF developed across the moving coil. So these are all some of the representations we made use of in our torque equation derivation. So M here, since we have two coils, that develops mutual inductance due to the flow of current in these two coils. So that is represented by capital M. and here phi 1 represents the flux linking with the coil 1. So that can be represented by means of Faraday's law using this equation L1 I1 plus M into I2, whereas phi 2 is the flux linking with the moving coil and it is represented by L2 I2 plus M into I1. So here L2 is the self-inductance of the moving coil, I2 is the current flowing through the moving coil, M is the mutual inductance between the two coils, and I1 represents the current flowing through the coil 1, that is the fixed coil. So as I said earlier, whatever the electrical input we are applying at the initial stage at the fixed coil is made use of for moving the pointer, so there develops a mechanical energy. So mechanical energy plus energy stored. So since there involves two coils here, the amount of energy entering at the input stage is stored in these two coils. So a little bit of energy will be stored in fixed coil as well as in the moving coil. So the electrical input that we are applying at the input stage is made use of for moving the pointer in the pointer over the scale arrangement, and a little of energy is stored in the two coils. So this is the basic equation based on which we are going to derive the torque equation. So the electrical input is equal to mechanical energy plus energy stored. So first we shall derive the electrical input equation, then we shall derive the energy stored equation, from which we are going to find out the mechanical energy. Okay, so first we shall derive at the electrical input energy. So this is the electrical input energy is equal to E1 I1 dt plus E2 I2 dt. So here we are going to apply the electrical input, so that is equal to E1 I1 dt plus E2 I2 dt. Here E1 is nothing but d phi 1 by dt and E2 is nothing but d phi 2 by dt. So I am going to replace these two terms in this equation. So here E1, instead of E1 I am going to replace it by d phi 1 by dt. So already here we have dt, so these two dt gets cancelled out, so it will be I1 d phi 1 plus here 2. When we apply this d phi 2 by dt in the place of E2, this dt and dt gets cancelled out, so the remaining term will be I2 d phi 2. So in our equation the electrical input energy will be equal to I1 d phi 1 plus I2 d phi 2. So already we have derived the equation for phi 1 and phi 2. So I am going to replace the values of phi 1 and phi 2 here. So I1 differentiation of L1 I1 plus M into I2 plus I2 differentiation of L2 I2 plus M into I1. So in the next step, we are going to differentiate each terms one by one. Since the bracket is differentiation is outside the bracket, so we need to differentiate this term first and then this term. So I1 differentiation of L1 I1. Here there involves two terms L1 and I1. So we have to keep this L1 constant, then differentiate I1, then I1 constant, differentiate L1. So the equation will be I1 L1 dI1 plus I1 square dL1. Similarly, in the next term we have MI2. So we need to differentiate one by one. So I1 I2 dm plus m into I1 into dI2. That's what written here. I1 I2 dm plus I1 then we are going to differentiate these two equations, these two terms. So I2 differentiation of L2 I2. So I2 L2 dI2 plus I2 square dL2 plus I1 I2 dm plus I2 m di. So since the two inductances L1 and L2 are constant here, the differentiation of L1 and L2 will be equal to 0. So in these two places we are going to replace it by 0. So these two terms will be eliminated in the next step. So I1 L di1, so this is 0, so I am going to write this term next. So I1 I2 dm plus I2 L2 di2 plus this term is also 0, then I1 I2 dm plus I2m di. So this is our electrical input equation. So we have derived the electrical input equation. So in the first step we have written E1 I1 dt plus E2 I2 dt. In the place of E1 and E2 I am going to replace this d phi 1 by dt and d phi 2 by dt, and then we are differentiating one by one. So that's the electrical input energy equation. Then we need to find out what's the energy stored. Normally in inductors, when we make use of inductors, the change in stored energy can be written as 1 by 2 Li square. So based on that we need to derive the equation for change in stored energy. So it will be differentiation of 1 by 2 L1 I1 square plus 1 by 2 L2 I2 square plus m into I1 I2. So here we have three terms. Outside we have differentiation. So we need to differentiate these three terms one by one. So here when we differentiate 1 by 2 L1 I1 square, L1 by keeping L1 constant, differentiate I1 square, then keeping I1 square constant, differentiate this L1. So it will be I1 L1 di1 plus I2 L2 di2 plus I1 m di2 plus I2 m di1 plus I1 I2 dm plus I1 square I by 2 dl1 plus I2 square dl2. So this is the differentiation equation. Then we are going to simplify this equation in our next step. So it changes as I1 L1 di1 plus I2 L2 di2 plus I1 m di2 plus I2 m di1 plus I1 I2 dm. So when we simplify this entire equation, we could get it as the mechanical energy will be I1 I2 dm. So the resultant change in energy, that is here this mechanical energy equation will be mechanical energy equal to electrical input minus change in energy. So after subtracting these two equations, that is this equation and this equation, so I am going to subtract this equation with this equation. So the resultant equation for mechanical energy would be I1 I2 dm. So what's the mechanical energy involved here? So the mechanical energy is to deflect. So, suppose the pointer is in this position, it will be deflected over some angle theta. So that is represented by d theta. So for deflecting over an angle, it needs some force, that is represented by Td. So the mechanical energy is denoted by Td into d theta, and we have already derived what is mechanical energy. It is equal to I1 I2 dm. So we are equating those two equations. So Td d theta equal to I1 I2 dm. So we need the value of Td. So I am bringing this d theta to the other side. So it will be I1 I2 dm by d theta. As I said earlier, there develops three different torques: deflecting torque, controlling torque and damping torque. We are making use of these two torques in our torque equation, that is the deflecting torque and controlling torque. So the controlling torque is developed due to the presence of spring arrangement connected directly to the pointer. So that controlling torque will be equal to K into theta, where K is nothing but the string stiffness and theta is nothing but the deflection of the pointer. So our TC equation will be K theta, and at balanced condition this TD will be equal to TC. So we are equating these TD and TC equations. So I1 I2 dm by d theta equal to K theta. So here we need the value of theta. So I am keeping this theta on one side and bringing this k to the other side. The equation will be I1 I2 by k dm by d theta. So when we look at this equation, this k dm by d theta, these are all constants. So the equation changes as theta proportional to I1 I2. That is, the deflection of the pointer will be directly proportional to the current through the fixed coil and the moving coils. Suppose when this dynamometer is meant for measuring the DC values of currents, since the fixed coils and moving coils are connected in series, this I1 and I2 will be equal and it can be represented by capital I. So when we substitute it over here, theta proportional to I into I, so therefore theta will be directly proportional to I square. So in an electrodynamometer type instrument, the deflection of the pointer will be directly proportional to the amount of current flowing through both the coils, fixed as well as moving coils. Then if it is used for measuring the AC values of currents, we need to derive the torque equations. So here since the two coils are connected in series, whatever current entering at the fixed coil will be flowing through the moving coil also, but with minute phase difference. So if the current through the fixed coil is denoted by Im1 sin omega t, the same current will be flowing through this moving coil also, whereas the exists little bit phase difference, that is denoted by sin of omega t minus phi. So in our equation, TD is equal to I1 I2 dm by d theta. So I am going to substitute these values over here. So TD is equal to Im1 sin omega t into Im2 sin of omega t minus phi dm by d theta. So for measuring the AC values of current, it is measured over a particular time duration starting from 0 to 2 pi. So I am going to integrate this TD value over a time period 0 to 2 pi. So we get it as 1 by 2 pi integration 0 to 2 pi Im1 Im2 sin omega t sin of omega t minus phi dm by d theta d of omega t. With respect to omega t, we are going to integrate the above equation. So in our next step, when we integrate, this Im1 Im2 will be constant, taking it outside. So integration of sin omega t sin of omega t minus phi, after applying the limit 0 to 2 pi, it changes as cos phi. The remaining term remains the same, so dm by d theta. After integrating, there is no need for writing this term. So as it is, the equation changes as Im1 Im2 by 2 cos phi dm by d theta. So instead of Im1 and Im2, I am going to replace it by a constant value I1 and I2, which is nothing but the RMS values of currents I1 and I2. So the above equation is replaced here as I1 I2 cos phi dm by d theta. So this is the torque equation, TD equation, when it is used for measuring AC values of currents. So here, suppose when we replace this I1 by V by R, V1 by R, I2 cos phi dm by d theta. So this V by R, in this equation, this R dm by d phi, these are all some constant values. So the equation will be TD equal to V1 I2 cos phi. So when we look at this equation, this is nothing but the power equation for a AC circuit. So these instruments can be made use of for measuring the power also. Apart from measuring currents by by equating it directly with the currents, we can also measure the power in a AC circuit using the same instrument with little bit modification in the circuit. So these electrodynamometer type instruments are meant for measuring the AC as well as DC values of currents and voltages, and the major function of this electrodynamometer type instrument is for measuring the power entering in a circuit. So this is about the torque equation. So now we shall discuss about the advantages and drawbacks of this electrodynamometer type instrument. Now let's discuss about the advantages of using this instrument. So electrodynamometer type instruments can be made use of for measuring both AC as well as DC values of currents and voltages, and it's a highly accurate instrument and it is a more reliable instrument. Coming back to the drawbacks of using this instrument, it has a non-uniform scale arrangement, and the torque weight ratio in these instruments are also less. So this is a comparatively more expensive instrument since it is provided with two coil arrangements. So these are all the some of the drawbacks of using this instrument. And regarding its application, we can make use of these instruments for measuring current, voltage, and with certain modification in the circuit we can even measure power factor also. So this is about the electrodynamometer type instrument, and in our next video we shall discuss about the rectifier type instruments. For more videos, keep watching. Please subscribe and share. Thanks for watching.